we'll talk about the construction of CPA-secure encryption from pseudonym functions. And well, the construction that we've seen in the lecture is this one. You should remember this by now. Now I will rewrite this a little bit. Because I want to look at it as actually the construction where we choose a random R and then use the pseudonym function to derive a key for an encryption scheme. In this case, it's the one-time paired encryption scheme. Because this shows a nice little way of thinking about this scheme that we have. So essentially, these two are the same. I now just rewrote this one-time paired encryption here explicitly as a one-time paired encryption here, where the key is derived from the pseudonym function. And now my claim is that actually, instead of the one-time paired here, we can use any other eavesdropping-secure encryption scheme. So in a way, the pseudonym function allows us to upgrade any eavesdropping-secure encryption to CPA security. What I want to show is that if this encryption scheme here is eavesdropping secure and f is a pseudonym function, then the scheme here that we constructed, where encryptions look like this, and then key generation will choose a random pseudonym function key, and decryption looks like as you would think it would look like, then this scheme is actually CPA secure. So we're essentially upgrading from eavesdropping security, combining it with a PRF, and we get CPA security. This generalizes the thing that we did in the lecture, where essentially this is the theorem where the eavesdropping secure scheme is just a one-time paired. And then this is exactly the same theorem as you had in the lecture. Just this one is a bit more general. Okay, so we want to prove that essentially if we take any adversary, then the probability of it winning the CPA game against our new scheme that we're constructing, that probability should be 1/2 plus something negligible. So we're doing this as you would think. We start with an arbitrary adversary. Now the first step will be, we'll take the scheme that we have up here and we will replace the pseudonym function by a properly random function. This makes sense because this is what PRFs do. They behave somewhat like a random function, and in order to be more formal, they are indistinguishable from a random function. So we will replace this pseudonym function in here with an actual random function. And what we get will be like a conceptual scheme. So what we get replacing the pseudonym function with the random function is this scheme up here, where essentially we're now using a random function and we're storing this random function within the key k. As was already noted in the lecture, this is not an encryption scheme because the key cannot be generated in polynomial time. An actual random function takes way too much space to generate. But as a concept, we can use it and we can talk about it like it was an encryption scheme. And now the claim is that A will do just as well against our scheme as it will do against the conceptual scheme. More formally, so this is what I'm claiming, that the adversary in the CPA experiment against the scheme that we want to prove secure will do not much better or worse than against the scheme, the conceptual scheme that we came up with. Okay, and then the idea will be that this conceptual scheme will be much easier to analyze because there's no pseudonym function in it anymore. How would we prove something like this? Well, assume that the adversary A was way better here than he was here. And we want to prove that this is not possible, right? Because this distance should be very small. So if we had an adversary that does way better here than he does here, then we could use this adversary to distinguish the two worlds between the pseudorandom function and the random function. So formally we would construct a distinguisher D. This distinguisher would run the adversary A through a simulated version of the CPA game. Then we need to say how we answer encryption or how we encrypt stuff there. And D will do this by doing the encryption function, but replacing the call to the pseudorandom function with an oracle query. And then the nice thing is that if the oracle is FK, so the PRF, then D will, for A, it will look like A is in this world. And if it's the properly random function, that is the oracle for D, then it will look for A like it's in this world. Eventually, A will output two messages. D will choose one of them randomly and encrypt this message using the same encryption thing that it's been doing before. Then A will output a guess bit B prime. And then the idea is that D wants to use this hypothetical ability of A to do better in one of the two worlds. So it will output a bit that indicates whether or not A wins. So mainly that the bit B prime is equal to the bit B that D chose himself when he did the encryption of the challenge message. So then overall, if we do it like this, then the probability that D outputs 1 if it gets a PRF as an oracle, that is exactly the probability that A wins this game here. And the probability that D outputs 1 in case it gets a properly random function as an oracle is exactly the same as the probability that A wins this game over here, the right-hand side one. So then, because D shouldn't be able to distinguish the PRF from the random function, also A cannot win more in one of the two different worlds, because then D would notice this and would be able to distinguish the two worlds. Note that so far, the proof has been exactly the same as the one that we did in the lecture. In the lecture, we also came up with the distinguisher D, and they also have this conceptual encryption scheme that replaced the PRF with a random function. So what have we gained? Well, now we only need to look at the conceptual scheme, because we have proven that essentially the conceptual scheme is indistinguishable from the original scheme that we wanted to prove secure. And now adversary can do better in the conceptual scheme than it can in the scheme that we constructed. So after all, we only need to look at this anymore. So how well can a PPT adversary do against this conceptual scheme? So we only care about this probability now, that the adversary A wins the CPA game against the conceptual scheme. But remember that the conceptual scheme had a shortcoming. If we do use the same R twice, then trouble happens, because then we use the same key to encrypt something with an eavesdropping-secure scheme, and eavesdropping-secure schemes don't necessarily are secure if we use the keys multiple times. So an adversary, if our challenge ciphertext is using the R that was also used for some other encryption query, something may go wrong. For this reason, we do a case distinction, whether or not this event happens. So we look at the event repeat. The event repeat happens if the R that we are using in the challenge ciphertext is the same R as any of the R's that we used for any encryption query. So we're looking at the probability where repeat happens, and we're looking at the probability where repeat does not happen. And then this first part we can immediately see is okay, because this repeat event, as we've seen in the lecture, is pretty rare. More specifically, it happens with probability at most Q of n over 2 to the n. So Q of n is the number of queries that A makes to the encryption oracles at most, and 2 to the n is the number of possible R's. So the probability for the repeat event itself is already pretty small, so we don't actually need to make it smaller by having this end part here, so we just remove it. And then we have that this first part of this probability of the sum here is already negligible. The only thing that's left to show is what this probability down here is. And in the lecture, this was a pretty easy part, because in the lecture, the scheme that we used to encrypt stuff over here on the top right, this was just the one-time pad. And the one-time pad is not just eavesdropping secure, it's even perfectly secret. So in this case, the following was easy to see. So just the definition of conditional probability. And then we knew that this is at most 1, so we don't care about it. And then this one, if the R does not repeat, then the key that's used for the one-time pad is perfectly random, because it's from a random function. And in that case, the one-time pad security guarantees just tell us that the challenge ciphertext is independent of the message. So the probability to win for an adversary in this case is just exactly 1/2. So essentially, the probability of A to win against the conceptual scheme would have been 1/2 plus this negligible part for the repeat event. And then this was close to the winning chance of A against the scheme that we want to prove secure, and then we would be done. We don't have it quite as easy because we don't necessarily use the one-time pad, we use any eavesdropping secure encryption scheme. So what we need to do is a reduction in order to show that this one here ideally is at most 1/2 plus something negligible. Again, I'm using the trick that I remove all of the absolute values from the security definitions. So this is a reduction. So what we're doing is we're taking this adversary A and we can use it to construct an adversary A prime against the eavesdropping security of the original scheme. So the scenario that A is in is the following. So we have A prime that plays against the challenger with the pi eavesdropping scheme. And then we have the adversary A that thinks it's playing against the conceptual scheme, and A prime will take the role of its challenger. Now we need to define what A prime does. So it runs A, this is a given. A will ask encryption queries because it thinks it's in the CPA game against the conceptual scheme. So it will ask queries for encryptions of plaintext PI. And now how can A prime answer those? You have an idea? Well, A prime can just choose a random R and then like kind of in its head simulate this properly random function f, and then it encrypts using f of r. So notice that f of r is not actually a thing in the scenario of A prime. There's no random function, and A prime doesn't have the runtime to actually write down a random function. But the trick here is pretty simple. You will see this in the lecture again and again. Essentially, when I write fr here, I just mean if that's the first time that you see r, pick a random string for it and call this f of r. If you've seen this r before, then reuse the same value as you did before. And this is exactly the right distribution of things that A would expect. So A would see a randomly chosen r and then an encryption under f of r, where f of r, because it's a random function, we can just replace with an actual random string. Then at some point A will output 2 messages. Now what does A prime do with those? Do you have an idea? Yeah, right, so it will give those to his challenger. And what we get back is an encryption of MB. And the key for this encryption will be, well, unknown. It will be the key that the challenger chose. But we don't need to know the key. We can just call this C. And then we just give the C to A, and we just come up with a random R. Let's call it R star, and give that to A. Then for A, this looks kind of okay again. There's a random R in front, and then there's something that is an encryption under a random key. And then A would output a guess B prime, and A would also just output the same bit. So all of this works perfectly. The only thing that is kind of unfortunate, I guess, is that there's one situation where A may notice that it's in a simulation. Namely that if this R star that we use here, if that one has actually been used before in one of these encryption queries up here, then in this case the simulation kind of breaks. We don't have the exact right distribution of things anymore if one of these encryption queries used R star. Then, because then A would expect this challenge ciphertext to be under the same key as the encryption query that used the same R. But it probably won't be. However, if R star is not used in any of the encryption queries, then everything is perfect. For A, it will look like it's playing against the conceptual scheme. And overall, if A outputs the correct bit B prime, then also A prime will output the correct bit B prime. So to be a bit more formal about this, these two probabilities are equal. And then, well, what we know is that this event here should happen with probability 1/2 plus a little bit of negligible. So then overall we get what we want. So overall we get that the probability that A prime wins against the eavesdropping scheme should be 1/2 plus negligible. As a consequence, the chances of A against this conceptual scheme, in the case that they don't repeat, or the event that both happens, it doesn't repeat, and he wins the conceptual game, this is negligible. Sorry, it's 1/2 plus negligible. I'm doing this error a lot today. So then we can get back up here, and we will see that we actually have shown the thing that we wanted to show. So to summarize, we started with a scheme that we wanted to prove secure, and we came up with a conceptual scheme where we replaced the PRF with a random function. Then we proved that there's actually no real difference between the conceptual scheme and the original scheme. So no PPT can distinguish whether he's playing against the one or the other. So then in the following, we could also just look at the conceptual scheme. The conceptual scheme, we had to do the case distinction, whether or not the R repeats. And if the R doesn't repeat, then we were able to come up with a reduction to the security of the eavesdropping game. And only this last part, this reduction using A prime, this one was not used in the proof in the lecture. All right, if you want to make sure that this makes sense, you may cross-reference it with the proof that we did in the lecture and kind of try to map where in the lecture this conceptual scheme, what it looks like, how this distinguisher works, and then note that this whole playing with probabilities over here, that this was mostly not necessary because in the lecture it just boiled down to this here. Thanks for watching, and then see you next time.